Okay, this is going to be a lesson about how to diagonalize a matrix. So we're going to look at diagonalizing a matrix. So let me just remind you of what a diagonal matrix is. So a diagonal matrix is a matrix that has zeros everywhere except on the leading diagonal. So here is an example of a diagonal matrix. Now, it turns out that diagonal matrices are really quite useful. I'm going to give you a couple of simple examples. And because they're useful, what we try and do is put a matrix in a similar way as we can to a diagonal matrix. And I'll explain what I mean by that in a minute. So here's a couple of reasons as to why we care. So why care? So why bother with them? Well, diagonal matrices are really useful in solving equations. So for example, if I had this system of equations, hopefully you can see that the solution to this, let's make that 4, let's make that 12. Hopefully you can see that solution to this would be 2x equals 4, so that means x is equal to 2, and 3y equals 12, so y is equal to 4. So they're easy to solve. So one reason is they're easy to solve. And what I mean by that is simultaneous equations. So that's one reason why we could bother. Another reason why we might bother is that they're easy to take powers of. So for example, 2, 0, 0, 3 to the power 4 would be the same as 2 to the power 4, 0, 0, 3 to the power 4, which is the same thing as 16, 0, 0, 81. I'll let you perform the multiplication if you really want to convince yourself, but because it's a diagonal matrix, taking powers is really easy. So easy to take powers of. What else? Another nice fact is that eigenvalues are dead simple. So got easy eigenvalues. So stick with the same one, 2, 0, 0, 3. So the characteristic equation of this will be the determinant, or if I call this A, determinant of A minus lambda I is equal to 0. So that would be giving me 2 minus lambda times by 3 minus lambda equals 0. So lambda's 2 and lambda's 3. In other words, they're the on-diagonal numbers. So there's 3 reasons why we could be interested in diagonal matrices, and I want to put there are others, plus others, too many for me to sort of go through now. Yep. And others. Okay, so diagonal matrices are really useful. Now, before we go on, I want to kind of rethink our perspective of matrix multiplication. So this is going to be a side note. And what I wanted to do is rethink matrix multiplication. Because if you're not thinking of matrix multiplication in this way, then it might throw you. So the way I'm going to do this is I'm going to give you an example. So suppose I've got a matrix A, which is given by 2, 4, 3, 8, and a matrix B, which is given by, let's call it P actually, because that'll link nicely when we do later on. So let's call it a matrix P, which is 1, 0, 3, 2. So I can compute the product of these matrices really simple. So I'm going to do 2438 times by 1032, and that's going to give me, well, let's do it. We're going to do 2 times 1 is 2, plus 4 times 3 is 12, so 2 plus 12 is 14. The next entry here will be 3 times 1 is 3, plus 8 times 3, which is 24, so 3 plus 24 is 27. Over on this side, we're going to have 2 times 0 plus 4 times 2, which is 8, 3 times 0 plus 2 times 8, which is 16. So the product, AB, or AP even, so AP is equal to that. So what I want us to do is just observe, if I do 2438 and I times it by 13. So I could just take this matrix here and times it by this column here, then what I get is 2 times 1 is 3, sorry, 2 times 1 is 2 even, 4 times 3 is 12, 2 plus 12 is 14, 3 times 1 is 3, plus 24, which is going to be 27. So in other words, this entrance here is precisely this matrix acting on this first column. Okay, let's have a look at the second one. 2438 times by 02. You can check, this is going to give us nothing 8, nothing 16, but notice this is the second column. Okay, so in other words, to sort of summarize this, this is a key fact. The product AB, so the product AB is formed by applying the matrix A to the columns of the matrix P. Okay, so, and then we're putting them together. So this here, this column here, the product, this column here is precisely this matrix acting on this column, and this column here is precisely the matrix acting on the second column. So let me kind of spell it out. So if I've got a matrix A and a matrix P, now the matrix P I'm going to say is consisting of some column vectors, P1, P2, P3. So this notation here, it means here's the matrix P, and the matrix P is formed by these column vectors. So each of these P1, 2, 3, they're column vectors. So the PI are column vectors. So what I'm saying is, then the product AP is exactly the matrix A acting on the column vector P1. The next entry would be the matrix A acting on the column vector P2. And the next one will be A acting on the column vector P3. So the product AB is formed by applying the matrix A to the columns of the matrix B in turn. Maybe I should add in turn. So there we go. So even though this looks like a bit weird, it really is just a column vector. So if you think here, we've got the matrix A, the matrix P. So maybe if we just start with an example, so this would be A and this would be P. So this would be the matrix A applied to P. Okay, so that's kind of a little bit of a sidestep, but it's important to get that in your brains so that we're going to apply this fact now. Okay, so let's recall what we mean by the eigenvectors of a matrix. Eigenvectors of a matrix. So Well, we mean if we can solve the system ax, where x is a vector, equals lambda, where lambda is a scalar, times x. In other words, the matrix does nothing but scale the input vector. So the matrix just scales. So let's define a few things now. So let's just consider a 3 by 3 case, but we could think of this for any n by n, but let's consider a 3 by 3 case. So a 3 by 3 matrix A. I'm going to do the rest of the working in for 3 by 3 matrices, but it could generalize easily enough. So suppose A has eigenvalues lambda 1, lambda 2, lambda 3, okay? And the associated eigenvectors, remember there'd be infinitely many for each one, but let's just think of the eigenvectors. Let's call them P1, P2, P3. So specifically what I'm saying here is, I'm basically saying that A applied to lambda 1, sorry, A applied to P1, the A applied to the vector P1 will give me lambda 1 times the vector P1. And each of that would be true for each of the i's. Okay, let's now form a matrix, capital P, whose columns are the eigenvectors. And all will become clear as to why I'm going to do that. So specifically, capital P is going to be P1, P2, P3. And here I've already said these Pi are eigenvectors. So the Pi are eigenvectors. Okay. So we've got this set up here now. What we're going to do is we're going to consider now, so we know we've got a matrix A, it's a square matrix, it has these eigenvalues and corresponding eigenvectors, and what we're saying is, let's form some new matrix P whose columns are the eigenvectors, okay? Now the reason for doing that is that we're now going to consider the product, so let's consider the product AP. Well, from our earlier work, we know that when we do a matrix multiplication, it's like applying A to the columns of P in turn. So in other words, the solution to this product will be A times P1, A applied to P2, A applied to P3. As I say, this was from our first note. When we're doing the product AP, it's like applying A to the columns of P in turn. I'll maybe highlight that up here somewhere. So AP applies, I'll write that a little nicer. So capital A, capital P, that applies A to the columns of P in turn. That's exactly what we've done here. So this is just a column vector. This is just a column vector. This is just a column vector. But, and here's the reason for creating this matrix in the first place. We chose these vectors, not any vectors, they're eigenvectors. So we know now that we can now swap out AP to lambda P because it's an eigenvector. So we can now say this product AP is going to be lambda 1, P1, lambda 2, P2, lambda 3, P3, because these were specifically eigenvectors. This wouldn't work for any kind of vector, we're talking eigenvectors. Now then, this is good news now, because lambda 1, lambda 2, lambda 3, being eigenvalues, they're just scalars, and so we can factor them out. So if we factor them out, we're going to get this. So we're going to end up with P1, the column vector P1, which is an eigenvector, P2, the column vector P2, which is an eigenvector, P3, the column vector P3, which is an eigenvector. Now, this is going to, we could factor out the lambda 1. It's going to give us 0, 0. We're going to factor out a lambda 2. Lambda 2 is going to give us a 0, and we're going to factor out a lambda 3. Okay, so this matrix product AP is this column, this matrix here, which is none other than the matrix P that we formed before, times by this new diagonal matrix. So let's let capital D equals this diagonal matrix whose entries on the diagonal are the eigenvalues. So if I write it like this, 0, 0, lambda 3. Now, so if we let D equal this matrix, which is a diagonal matrix, and the entries on the diagonal are the eigenvalues, then we could write the product AP as AP is equal to, well, this is the matrix P already, and this is the matrix D. Okay? So we've got this statement now, AP is equal to PD, where P is the matrix of eigenvectors and D is the diagonal matrix of eigenvalues. Okay, so we've just got one final step now. So let me kind of move this along a little bit so we don't have to start a new page. So finally, and here's the key part. So finally, we've got AP equals PD, but we could apply the matrix. P inverse on the right-hand side. Okay. Now I've assumed that P has an inverse, and we'll talk maybe a little bit about that afterwards. But we could apply the matrix P inverse to the right-hand side. So we could right multiply by P inverse. So we're going to end up with AP P inverse is equal to PD P inverse. But P times P inverse is precisely the identity matrix I. So we're going to have A capital I equals PD P inverse. But if I apply the identity matrix to any matrix, I get back out the matrix that I wanted. So this matrix here, this PD P inverse, we have diagonalized the matrix. Now, obviously, or maybe not obviously, P and P inverse are not diagonal matrices, but D is. So that's what we mean by diagonalizing the matrix. So this here is the diagonalized form. Okay, so we've found the diagonalized form of the matrix. Okay, so I'll do a quick example of this, and then we'll look at some more of the technicalities of it, as into when it could go wrong. Okay, so if we want to diagonalize the diagonalized form of matrix is PD P inverse, where P is the matrix of eigenvalue vectors, D is the diagonal matrix of eigenvalues, and P inverse is the inverse of P. So let's go for a specific example now. So let's diagonalize. So let's diagonalize. Let's make a nice matrix that's fairly tame to do. So let's do 2. Oh, maybe I'll write that a bit nicer. So the matrix. Let's diagonalize the matrix A, which is 2, 0, 0, 0, 1, negative 2, 0, negative 2, and 4. Okay, so we're going to diagonalize this matrix here. So to do that, we're going to need the matrix P, which is going to be the matrix of the eigenvectors. So we require, first of all, the eigenvalues. So step 1 is going to find the eigenvalues. So, and then step 2 will be the eigenvectors. So we need the characteristic equation. So recall the characteristic equation is going to be a minus, or the determinant of, I'm not going to go into why this is now, but I'll do another video on that. Determinant of a minus lambda I is equal to 0, where 0 is just a number. So specifically, this will be 2 minus lambda, 0, 0, 0, 1 minus lambda, negative 2. Or determinant of this, I should say. 0, 2, or negative 2, 4 minus lambda equals 0. Okay, well, I chose the matrix to be really nice because finding the determinant isn't a hassle. I didn't want to create a matrix where the determinant was going to be some big hassle. So if we expand about this, this here, we're going to end up with the characteristic equation being, so this is going to be 2 minus lambda times by the determinant of this minor matrix. So that would be times by 1 minus lambda times by 4 minus lambda, subtract, well, minus 2 times minus 2 is 4, equals 0. So that's just by expanding by a column. Then, well, let's expand and tidy this up. We're going to end up with essentially 2 minus lambda. What will this be? This is going to be 4. Take a lambda, take a 4 lambda, plus a lambda squared, take a 4, equals 0. But we're going to have the 4's are going to cancel, and we can simplify to get 2 minus lambda times by lambda squared, take 5 lambda equals 0. But now we can factor out a lambda from this term here to give me lambda times 2 take lambda, which is then lambda take 5. Have I done that right? Okay, equals 0. So now this is going to give me, eigenvalues of lambda equals 2, lambda equals, 0, lambda equals 2, lambda is equal to 5. So now we've got 3 eigenvalues. So straight away we can form, maybe do that here in different color. So 2, we can form D, which is the matrix of eigenvalues. So we can specifically say D is equal to 0, 0, 0, 0, 2, 0, 0, 0, 5. Okay. Okay, so we've got the eigenvalues. Now we're going to need the eigenvectors. So I'm going to need more space for that, I think. So let's have a new page. So the eigenvectors. So we've got the case where lambda is equal to 0. So let's tackle that one first. So then for finding the eigenvectors, you need to solve the system a minus lambda I times the vector x is equal to the vector 0. Okay, again, I'm not going to go back into that, otherwise the video would carry on too long, but we need to solve this system here. So that means basically sub in the lambda and then solve. So a minus lambda I, well, let's just remind myself what the a is, so I've got a reference. So a is equal to 2, 0, 0, 0, 1, negative 2, 0, negative 2, 4. So reminding myself on that. So I've got a minus lambda I in this case will be, well, I'm going to take 0 off the leading diagonal, which is going to leave it exactly as it is. So 2, 0, 0, 0, 1, negative 2, 0, negative 2, 4, times by some vector x, y, z equals the 0 vector, 0, 0, 0. Okay, so we can simplify this. I mean, there's a few ways of proceeding here, but the way I like to do is just to reduce this matrix down a bit and then read off when I feel like it. So here, what I'm going to say is that new row 3 of this matrix here, so the new row 3, so row 3 star is going to be equal to row 3 take away 2 times row 2. Okay, so if I times this one by 2, and then add on even. If I times this by 2 and then add it onto the next one, I'm going to delete the bottom row. So this will give me 2, 0, 0, 0, 1, negative 2, 0, 0, 0 times by x, y, z equals a 0 vector. So there's a couple of things we can read off from here. We're going to have 2 times x is equal to 0. So that means x is equal to 0. That's nice. We're going to have y take 2z is equal to 0. Y take 2z is equal to 0. And that's pretty much it. Because this bottom row is essentially now, we haven't got any more information. So we're going to have to assign a variable to one of these, or assign a parameter to one of these, to y or z. So if I say, let's let z equals some variable t, so this would become y take 2t equals 0. Then we've got y is equal to 2t. So combining these facts here, I've got the vector x, y, z is equal to, well, x is equal to 0, z is equal to t, and y is equal to 2t. Now I can factor the t out of this vector here, so this is going to give me 2 times the vector 0, 2, 1. So what this is essentially saying is all the eigenvectors associated with lambda equals 1 are spanned by the vector 0, 2, 1. So let's choose this as our principal eigenvector. Okay, so we'll choose this as our eigenvector. So we'll have the eigenvector as 0, 2, 1. Okay, but we could have chosen a different value of t and then got different eigenvectors, but we'll stick with that. So that's one of them. Let's copy this down and now I'll delete and do the next one. So we've done the case where lambda is equal to 0. Let's do where lambda is equal to 2 now. So what will that give us? Lambda is equal to 2. So a minus lambda I, well that will give me now 0 here. So 0 is on the top. There's going to be a negative 1 there. And there's going to be a 2 here. So that matrix times by x, y, z is going to give me the matrix 0, or the 0 matrix. Okay, so what can we do here? Well, I could times this by 2, and what could I do? I could times it by 2, and then subtract it from the bottom one. So I could maybe say row 3, the new row 3, so row 3 star is row 3, take 2 lots of row 2. So that would give me 0s on the top. The second row wouldn't change. So it's not changing. And then, well, if I take away 2 lots of negative 1 off here, that's going to give me 0. If I take away 2 lots of that, it's going to give me plus 4. It's going to give me 6. Okay. X, Y, Z is equal to 0, 0. And now we just piece together the information that we get. Well, straight away we've got 6z's equal to 0. So that means z's equal to 0. So that's the first thing. We're also going to have minus y minus 2z equals to 0. But z's equal to 0. So that's going to give us y is equal to 0 too. And x is a free variable. Okay, x could be what it likes. It's not going to change anything because the coefficient of x is always 0. So x isn't going to do anything. So we could say x is equal to some parameter t, where maybe t is some real number. Okay, so x is some variable t. So that's going to put these facts together. We've got x, y, z is equal to, well, x is this free parameter t, y is equal to 0, and z is equal to 0. But we could factor out the t to get 1, 0, 0. And then we have all the eigenvectors are spanned by 1, 0, 0. So we've got the eigenvector 1, 0, 0. Okay, so I'll copy this down and do the last one. So it's quite a lot of work for this. I mean, it's quite good that we do have electronics to do all this kind of heavy lifting, but it's good to understand where it all comes from. So I've got lambda equals 5 now, and so this is going to take 5 off the leading diagonal, so that's going to give us negative 3, 0, 0, 0, negative 4, negative 2, 0, negative 2, and take 5 off there is going to give negative 1, times by the vector x, y, z is going to give me the vector 0, 0, 0. Okay, so again, I can tidy up this a little bit. So maybe I'll say, let me half. So I'll do the new row 3. So row 3 start is half, it's going to be the old row 3. Take away half of the old row 2. If I half this row, that means negative 2, negative 1. And if I subtract negative 2 from negative 2, that's going to give me 0. So that's going to give us negative 3, 0, 0, 0, negative 4, negative 2, 0, 0, 0, x, y, z. Now, I'm not claiming that my way of finding the eigenvectors is the best way or anything. It's just the way I always do it. So what's this saying? Well, we've got negative 3 times x is equal to 0, so obviously x is equal to 0. We're going to have negative 4y, and take 2z is equal to 0. Well, I could cancel this down to negative 2y, take z is equal to 0. And then I can assign a parameter. So maybe I could assign y is equal to some parameter t, where t is some real number. So this is going to give us negative 2t take z equals 0, and so z is equal to negative 2t. So combining the facts, x, y, z is equal to, well, x is 0, y is t, and z is negative 2t, so negative 2t. But now I can factor out this to be the same thing as, maybe I'll move it over here a little bit. So I could factor this out to be t times 0, 1, negative 2. And so we found our final eigenvector. So an eigenvector of 0, 1, negative 2. Okay, so we've kind of got all the information now, just need to piece it all together. So new page. I have to quickly go back. So we had the D matrix, which was the matrix, let me just remind myself, right up here it was. Okay, it's going to be 0, 0, 0, 0, 2, 0, 0, 0, 5. That's the matrix of the eigenvalues. So the corresponding eigenvectors, so now we can make the matrix P, which is going to be, so the eigenvector for 0 was 0, 2, 1. So that's going to be 0, 2, 1. The eigenvector for 2, what's this one, is 1, 0, 0. 1, 0, 0. And the eigenvector for 5 was 0, 1, negative 2. 0, 1, negative 2. Okay, so recall that the diagonal form of the matrix A is going to be equal to P, D, P, inverse. So this would be P, which would be 0, 2, 1, 1, 0, 0, oops, 0, 1, negative 2, P, times by D, which is this matrix here, 0, zeros on the top, 0, 2, 0, 0, 0, 5, and then the inverse of 0, 2, 1, 1, 0, 0, 0, 1, negative 2, the inverse of that. And I'm going to stop here because otherwise we're going to hassle about finding the inverse of this matrix, and I really don't fancy doing that. But we've kind of gone for the whole point now, is we've got, this is a diagonal matrix. And this whole form is useful, as we'll mention it. If I wanted to do a to the power 4, well, what that would be is it would be p d p inverse to the power 4. Now, if I was to write this out, that would be p d p inverse, p d p inverse, p d p inverse, p d p inverse. Now, notice that sandwiched between the d's, the p inverses and the p's are going to cancel. So this is going to give me p d to the power 4 p inverse. And note, or recall, that powers of diagonal matrices are really simple to work out. So powers of diagonal matrices is really simple, so that's kind of worked out nicely. Okay, so where do we go from here? Kind of a summary, and not a summary, kind of thinking of it. Can you always do this? Is maybe a question. Can you always diagonalize a matrix? Well, the answer to this question is no. Okay, you can't always diagonalize a matrix. Specifically, you need enough eigenvectors, or we need enough independent eigenvectors to form the matrix P. And sometimes that's not possible, okay? So let me give you an example of some case where it is possible and one case where it's not possible. So let's do a simple, quick case now. Let's consider a really simple example now. The matrix A, which is 2, 0, 0, 2. So it's already a diagonal matrix if you want. Well, straight away you can see the characteristic equation of this is going to be 2 minus lambda times 2 minus lambda equals 0. And solving that's going to give us lambda equals 2, but it's a repeated, it's going to be a repeated root. So we say that's an algebraic multiplicity of 2, because it's either 2 or 2. Okay. Now then, when we want to now form the a minus lambda I times the vector x equals 0 vector, well, I'm going to take 2 off the diagonals, which is essentially going to give us 0, 0, 0, 0 times by xy equals 0, 0. Well, essentially, the x and y in this case can be anything you like, because it's just going to be all times by 0. So x and y can vary, and both vary independent of each other. So let's assign x equal to a parameter. So let's just say x equals s and y equals t, where s and t are both real numbers. Okay. So then essentially now we've got xy equals st, but I could write that as s times 1, 0 plus t times 0, 1. And here's the thing. Even though the algebraic multiplicity of the root was 2, we've got the geometric multiplicity as well being 2. So despite the fact this kind of only came up with 2, lambda's equal to 2, we still have 2 independent eigenvectors, namely 1, 0, 0, 1. Okay, so we have enough vectors here to form P, and so we can diagonalize. Let's have a look at one that's similar to that, but actually fails. So I'll do this in red now. So if I do, let's say the matrix A is 2, 2, 0, 2. So again, it doesn't take too long to realize that 2 minus lambda times 2 minus lambda is the characteristic equation, and so lambda is equal to 2 with algebraic multiplicity 2. Big multiplicity, where? Try that again, with algebraic multiplicity 2. Okay. So how's this changed? How's this any different from the last one? Well, again, now we've got to form our A minus lambda I times the vector x equals 0 vector. So if I take 2 off the diagonal, it's going to give us 0, 2, 0, 0 times by xy equals 0, 0. So from this, we're going to end up with 2y equals 0, and so y is equal to 0, but x is still free. So we can have maybe x is equal to t, where t is some real number. So we could say that xy is equal to t and y is equal to 0. Well, then we could factor out the t and get 1, 0. But here's where the thing fails now, because the eigenvectors are spanned by this one. There's only one eigenvector. So there's only one eigenvector. So the geometric multiplicity is not the same. Spell it right now, hang on. Eigenvector. So the geometric multiplicity the same. There's not enough vectors to do it. Okay. Okay, so there's only one eigenvector, so we can't span the space, if you like. Okay, this matrix is said to be defective. Okay, it's a defective matrix. We can't form the matrix P, and so we can't diagonalize. Well, if we try to form P, we'd end up with this, wouldn't we? 1, 1, 0, 0, and like, how are we going to factor the things out from there? It's going to fail, isn't it? Okay, so we can't form P, so this doesn't diagonalize. So I'll finish off with a little summary now. So to summarize, so if we've got a matrix A with eigenvalues lambda I and eigenvectors pi, then we can form the matrix capital P, which is made by the columns of the pi's. So let me just kind of make that a P1. So P1, P2, Pn in the n by n case. We can form P inverse. And so A is going to be equal to PDP inverse, where D is the matrix of the eigenvalues, lambda 1, lambda 2, lambda n. Okay? This will only work if there are enough vectors. And I've shown you an example before that there aren't always enough, so it's not possible to always do. Okay? So sometimes the matrix does not have enough independent eigenvectors. So maybe we should say independent eigenvectors. So if it doesn't have enough independent eigenvectors, then you can't diagonalize, you can't form the matrix P, and it will all fail. However, this whole idea can be extended to there is a next step, but I'm not going to go into it today. There is a next step. Let me write that down. There is a next step. We can consider the idea of a generalized eigenvector. Now, I'm not going to go into that now, but essentially you could say, well, an eigenvector is where you apply a matrix to a vector and you get some scaled version. Well, a generalized eigenvector would be, well, what happens if you apply a matrix more than once to a vector and eventually you end up with a scaled version, okay, which is a slightly different concept. Okay, well, I think this video has got enough content, really. As much as you can, wherever possible, when you're actually doing the diagonal matrices and things, use a calculator. Wherever possible, use technology, because this takes ages. Wherever possible, use technology. Well, hopefully that's been an overview and that's helped people.